So yes, my name is David Watkins. I have been at Columbia now for 8 years, but that includes undergrad. I research robotics at Columbia's robotics lab. And I'm going to show you what I've been doing during my PhD. Working with robots is kind of an interesting problem because it's not even close to being solved. So what you're going to see today might seem a little bit simpler than it really is in real life. And I'm going to kind of walk us through why something as simple as picking up an object and manipulating it is not solved yet. And hopefully I can click through my slides. So quickly, just to go over who am I and what a PhD student is, because I think that's kind of the whole point of this series of talks. I'm an entrepreneur. I've started my own company called Odify, which was supposed to help solve some cryptocurrency stuff. I don't recommend going into cryptocurrency, just general advice. I'm a researcher, and I've gone to several different conferences to show off research I've done. Stand-up comedian. I've performed at Gotham Comedy Club, Broadway Comedy Club in New York City. I've flown planes historically. I play guitar, and also I build my own computer. So I do a lot of different things, and I think one very important part of doing a PhD is that you don't just do research. You have to try other things. You have to see what you like, and it's a good opportunity, just like colleges, to kind of figure out what kind of niche in the world do you want to carve for yourself. And so I'm going to quickly go over the abstract of what I'm trying to do with my thesis here and what I plan on defending in December. And I want to first off start by saying that mobile manipulation is a really challenging problem. We have not solved the problem of a robot going to a location and then picking something up and manipulating it. And many of the previous works rely on heuristic rule-based strategies, such as if the thing I'm looking at is yellow, I'm going to now pick it up or put the robot hand at that location. We can overcome these shortfalls that most robotic solutions have fallen into by using what I'm sure a lot of you are familiar with: big data, deep learning, and simulation. What does that mean? Well, I can collect large amounts of data now that I wasn't able to before because we have access to more robust simulators that didn't exist only 3 years ago. And we can also capture more realistic sensory data. So if I put a camera in a simulator today, it's going to look a lot more like the real world than it did 10 years ago, when it might have looked more like a Pixar movie or worse. And because we can capture so much more data, we can handle more corner cases that we weren't able to before. And so the overview of my proposed solution to try to take advantage of simulators and go from one room to another, manipulate an object, is first we have a robot agent start in a location and navigate to a particular goal using a camera sitting on its face and just navigating to a particular goal location that we provided using various software that we've written. We then, once we're at the object, try to perform some kind of shape understanding to predict parts of the object that we might not be able to see. If I look at a cup or a camera or a computer, I might get a partial image, but I need to predict what the full geometry is so I can actually manipulate it. Performing some kind of refinement of that shape. So because we're relying on a robot that can move around, we can move to a different view that might give us more information to then manipulate the object. And then plan a grasp using that geometric prediction. So how am I going to put the robot hand relative to the object to actually pick it up and move it around? So the state of the field so far, in 2017, a next best view planning algorithm came out where they have this robot that can go up to an object, take a look at it, and they have a simple cylindrical model to identify where is my next best position to look at the object to get a better recognition of it. So it's trying to recognize the object using a database of objects that it already has. It's trying to evaluate the visibility of the object and how visible it will be in the next position. But because it's using the cylindrical model, it's not really taking advantage of the fact that cameras can move up and down, and the whole camera assembly can move up and down. And it would be better if you used a spherical model to identify good recognition candidates. And it doesn't handle any object geometry that's not in the database of objects. So it's only going to handle things it's seen before or that we have modeled in a database somewhere, which really does not lend itself well to the real world, where things can change just because they fell on the floor, and people move things around and color them differently. And we want more robust robotics. Another paper that came out very recently was handling strawberry harvesting in a field, and they had this very sophisticated custom gripper that they made to specifically grab strawberries. In order to navigate from position to position, they were using something called SLAM, which is simultaneous localization and mapping. That it basically, what it does is I have a map of my environment, and I am trying to find a path from point A to point B. And it just uses very simple algorithms, most of which you might have learned in analysis of algorithms, to find a path from point A to point B, and is using segmentation to figure out where the strawberries are. So if it's red, that's where the strawberry is. It's really nothing particularly sophisticated. But even though it came out in 2019, it still doesn't use deep learning. It still isn't considering novel objects. And this is really state-of-the-art next best view planning, grasp planning that exists today. And it also does not take advantage of semantic information other than the fact that red probably means strawberry. Another paper that came out in 2019 is this paper called Generalized Object Permanence for Object Retrieval Through Semantic Linking Maps. It's a really fancy way of saying, once I've been in a spot, recognize that that object's in that spot. And it's trying to use some predictive ability to figure out whether certain pixels in an image are coordinated with an object of interest. So we're using object recognition to find a 6DOF pose for an object on a surface. And 6DOF here just means XYZ for the position, RPY for the rotation. And degrees of freedom is DOF. It uses a belief network to find inter-object relations. That just means that if an object is sitting on a table, that there's going to be some kind of graph representation that says object on table. And it utilizes the semantic information of the image to label the objects as they are in the environment. It's using SLAM for environment navigation, so it's not taking into account any advancements in deep learning for navigation that we have, and it also doesn't consider anything outside of an object database. So my first piece of novel contribution that's forming my thesis is Visual-Semantic Navigation. And what am I doing? I am using RGBDS visual input alone. RGBDS stands for color, and then the D is depth, and then the S is semantic. And we're taking into account the previous 5 images that the robot's seen as it's navigating through a path. We provided a panoramic target so that at the goal location, it has more context as to what it needs to find. We're using real-world data captured via simulation to navigate and train an agent to navigate through these environments. And we're using expert trajectories captured using Dijkstra's algorithm to find point A to point B, what the most optimal path while avoiding collisions in the environment is. And I have some more examples of those expert trajectories like this one, where it starts off in this room, walks all the way through a hallway, and gets to a final location. This particular example is taken from Stanford, which they scanned a bunch of their buildings for use for these kinds of problems. There are several different data sets that you might want to use when you're considering building this kind of platform. So there's the Matterport 3D data set, which is a series of real-world scanned homes that are semantically labeled. So a bed will be labeled a bed, a window will be labeled a window, etc. And they are really good for training these agents because they're exactly the kind of environments I want my robot to be able to navigate through. Additionally, there's the SunCG dataset, which a researcher at Columbia, Sharan Song, helped to create. This dataset is a bunch of homes that were created synthetically, and there's several thousands of these. So you really can get a much more robust dataset, but it is synthetic. So it's a bit more difficult to get a sim to real transfer because of that. And then finally, there's the Stanford 2D 3DS dataset where they have the same semantic labels. It's 6 environments, which is technically smaller, but the environments themselves are huge. These are really, really large buildings that are very good for evaluating the effectiveness of your algorithm traversing large paths. And I might want to use those data sets in different simulator environments. So there's the Gibson ENV simulator, which came out in 2018, which gives you a variety of different sensory outputs. There's the Minos simulator, which came out in 2017. And there's the Habitat simulator, which came out in 2019, created by Facebook to do navigation in these environments. All of these are very good, but one thing that the Gibson environment has over the other two is that it's also a physics simulator. So we're actually evaluating whether or not there are collisions in the environment, and it makes it better for doing these kinds of training tasks. And it will make more sense when I talk about grasp planning later. And so we have a few sensory outputs that's coming out of the Gibson environment. We have the active agent, we have the large space, we have the RGB or color frame coming out, and then we also have the semantics, the surface normals, and the depth information. And so we can have the agent move through the environment and the whole viewport changes. Now, one of the nice parts about Gibson, if you look at the color, is that it looks pretty good. It looks kind of like the robot's actually there. And that's because it's doing a transfer style, a style transfer GAN to actually enhance the image after the fact. So if you notice the red circle there is a hole captured in the simulator environment. And this will frequently happen when you use scanned real world data, is you'll have holes in renderings that you try to take from different viewports in the environment. And so they trained this model to patch those holes over and make the images more photorealistic after you render in the simulator. This makes it really important for trying to do sim to real transfer, because otherwise you will have your agent learning things that it cannot do in the real world. You'll never see a hole in the real world. And so I used these data sets to create a series of trajectories for the robotic agent to learn from. So these are several thousand trajectories created in each of these environments. These are in the Matterport 3D data set, so these are the real world homes. And then in the Stanford 2D 3DS data set, I similarly created several thousand trajectories where the robot will start to finish, and I capture images along each of these trajectories. And so how do I take advantage of these? I have a panoramic goal with a history buffer and a current view as input into a robotic agent. It sounds like somebody's not muted, but I will persevere. I then try to compress the state of that input image using an autoencoder. And so the autoencoder, what it does is it takes an RGBD image, which is color and depth, turns it into a smaller version of itself so that I only have the relevant information, and then it blows it up out. So I never have to create any custom training data. I'm just training it on the images I'm going to be using to navigate through the environment. These are things that you learn in a deep learning course, but it's just, these are methods that you might use to make data easier to use when you're training an agent. So once I have this autoencoder, I get that embedding representation. It's a smaller representation. And I pass that as input into a goal checker. And what the goal checker is going to do is it's going to take the panoramic goal and the current view and determine what probability likelihood am I done. And this is a simple multi-layer perceptron taking in the 8 panoramic images, the current view, and asking the question, am I done? And if at any point I get an answer, that's 1. I spin in a circle to get consensus and determine if I'm done. But if I'm not done, I have this policy model that's outputting a forward, right, or left command using the 8 panoramic images and the 4 previous images in current view to determine how best to move to get to the goal location. Which will then update the environment because, of course, the robot agent will move, which will then update the autocoder, and then the whole process kind of flows forward like that. And so the whole example flows very nicely when it just kind of works at the end of the day. And that was a very fun day when all of this algorithm I came up with actually turned out to be working. So the robot agent right there is spinning in a circle to determine if it's done. And some additional work that I'm planning on doing is adding semantic labels as an output of the autoencoder to improve the amount of information that the policy is able to acquire at runtime. So this is another example. So this agent was just given the panoramic goal that you see at the top and placed at that location at the beginning, that large blue dot, and it was able to successfully navigate to the goal location. And this is fairly long trajectory that was not observed during training. So it has never seen this panoramic goal before, but was still able to learn how to get there. Another interesting emergent behavior that we found while training is that these agents can actually correct for errors during trajectory. So you can see that the agent thought it would go down that corridor to get to the goal location, but that was the wrong turn and actually fixed itself to get there. So while it's slightly longer, we can feel a little more comfortable that it's robust to errors during execution. So some alternative methods that we wanted to compare against is using this software called RTAB-Map SLAM. And what it's doing is it's using RGBD, stereo, and LiDAR graph-based SLAM to navigate between 2 places. So it takes pictures along the way and slowly builds up a map that it can use to navigate to a particular location. But the software is limited in that it doesn't use RGBD-based goals. There's no color and depth that it can provide. So my panoramic goals are not able to be used here. And that's not very human-friendly. It's you and I don't describe somebody going to a particular location by saying move to 4020 in the building. We say go to the water cooler. And I wanted that ability for the robot to be a thing. And this software, which is used in the industry, it doesn't allow for that. Additionally, the software doesn't have any ability to do manipulation, which will come into play later. Another piece of software is it's the simulator environment called AI2Thor. And they use the Siamese actor-critic model, which is frequently used in reinforcement learning algorithms. They trained it in simulation, and then they translated the agent to work in a real-world environment. However, the agent requires an idealized GPS during training, so I need to provide it the absolute position in space, which my agent doesn't require that. It only required color and depth. And they only trained it on 26 rooms and not multi-room environments. So each agent that they trained, the 26 of them, will only work in the room that it's trained in. I can't say go to the other room from this room and have it successfully navigate there. And also the goals were only RGB based, so only color, and there was no depth added to it. And also it doesn't use semantic information. Another agent that came out fairly recently, but we haven't benchmarked against, is this Decentralized Distributed PPO agent that provided color depth and also an idealized GPS and orientation in the environment. And they were trying to show that you can use an RL policy by massively training these agents with 64 GPUs in the cloud. And they were flexing all of these great computers that they have access to at Facebook. They used 2.5 billion steps of experience. They used the habitat simulator as opposed to Gibson. But there are some problems here in that my method requires substantially fewer steps. We used in the order of magnitude of millions of steps to achieve very similar performance to what they were talking about. And also they relied on this GPS and compass, despite the fact that you don't need that to get similar performance. And they don't consider any manipulation tasks. So they're not trying to solve a particular problem. They're just trying to get to an XYZ position in space. But I do want to compare against them at some point. And so the experimental setup that we have is 400 holdout trajectories. These are trajectories that were not seen during training. We tested our work with an idealized GPS. So instead of using that goal checker model, we checked to see whether or not we've gotten there. If the goal checker were 100% accurate, SLAM, and then the Siamese actor critic model. We terminate trials when collision occurs with a wall or an object in the environment. And we can show that our method really does get there more reliably. So this is the simplest environment we used, which we called House 2. And we had a success rate of 98.75%. And very frequently, the other two agents were not able to get there very well. And the accuracy goes down for our agent as the complexity in the environment increases, but their agents perform substantially worse as the environment complexity increases. They just love running into walls for some reason. I'm not sure. And the most complex environment, why is it? Okay, there is a video there in the slide deck. I'm not sure why it's not showing up, but we will skip over that, I guess. So some of the metrics we use to compare these agents, one is called success weighted by path length. That's just measuring the shortest path distance from the agent starting position, a success binary indicator, and the number of episodes. It's trying to normalize the length of the path to compare between two agents where the raw value might not be as good of an indicator, where the raw length of the trajectory might not align super well with how best to compare trajectories. Additionally, we compared observed over optimal, which was a little bit more of an intuitive metric where we're just literally comparing the ratio of the length of the path observed to the shortest path length, only considering successful trajectories. And so we can show the performance results empirically here. So the success rate in House 2 was substantially higher for ours. So you can see that even if we don't use an idealized GPS, our goal checker model is only getting slightly worse performance. And the performance does drop off as the environment complexity increases, but our performance is still substantially better than state-of-the-art methodology in the field. SLAM really struggled in a lot of these environments, and I think it might be because we tried to force some level of an RGBD goal with a position, which is something I plan on evaluating, whether or not these results are true to form. We also have the success weighted by path length metric per model, and our performance is roughly 70% of the optimal trajectory in the case where we provided an optimal GPS, and then in the case where we did privative GPS, we have about 65% success rate. And then the observed over optimal SLAM was getting about 25, in the case where it was successful, the lengths of the paths were 25% longer where it didn't have access to the map beforehand. I've also performed some preliminary results on integrating semantic, and I'm showing slightly better performance when we have access to semantic information, and I plan on creating a more robust data set of more than 5 environments as my thesis continues. And so now that we've addressed navigation, how do we handle the object once we're in front of it? And so some initial work by Jake Varley in my lab, he graduated in 2018, was taking a look at what happens when we have a Kinect camera that generates a point cloud. We want to complete the object somehow. And so we segment the point cloud out of the environment. We'll turn it into a voxel grid, kind of like Minecraft, which is it's a very nice format for deep learning methods because it's a binary indicator of whether or not something's occupied or not. We can then output it as a voxel grid, use an algorithm called marching cubes to turn it into a mesh, smooth the mesh using Laplacian smoothing, and then plan a grasp on it using some software we have written in the lab called GraspIt. And this pipeline worked pretty well. It used 40 cubed voxel grid input and has a 40 cubed voxel grid output. But there have been some advances in this particular type of shape completion. This researcher named Bo Yang created this reconstructive GAN model, which takes a 64 cubed voxel grid input and outputs a 256 cubed output to get a more rich completion model. They used a GAN architecture to refine the completions, whereas our work before was only taking into consideration examples that we had already pre-computed. So it was never trying to handle the case where we're almost trying to deceive the agent, which is what GANs typically try to do using a discriminator. And additionally, the original work that we did not consider some novel training methods. And there's this methodology called no-GAN where you train the generator and the discriminator separately. And that's something I'm looking to do to get better results for the completion. And so when you're doing these kinds of deep learning methods for grasping, you might want to consider these particular data sets, the YCB object data set, which I swear there's an image there, but I guess it's disappeared, which is 28 unique 3D models of real world household objects scanned, like Clorox, Rubbermaid containers, Spam container. And then there's the GRASP data set by Jeanette Bogue, which is 590 unique 3D models of objects that you would expect to be able to pick up and manipulate. And so for our work, we have these 618 objects. We captured 726 views per object, and that translates to almost 450,000 depth images, which we have both the input and also the output expected for each of the objects that we can train these models on. And so in order to improve the accuracy of this, we can take advantage of the fact that we have robots that have cameras and can move in an environment. So we can capture an initial view, which is what both of Bo Yang's work and Jacob Varley's work were doing to complete an object. And then we can capture a secondary view. And how can we take advantage of our initial view to predict where best to capture that secondary view, which is where my next best view stuff is coming from. And concatenate those two views to get a better input to predict a more accurate completion. And one of the theories that I have is that just capturing the opposite side is not good enough. And very frequently you might not be able to access the exact opposite view that you might want to you might get just enough information by going maybe only 90 degrees around the object rather than the full 180. And so that voxel grid that we have, each of those voxels has a probability of being occupied. And we can figure out the region of highest uncertainty, the region of that voxel grid that is closest to 50%, to find a next best view and then capture a secondary view to enhance our completion. And so some next best view algorithms that have existed historically. So in 1985, they created this spherical model where you have this sphere of viewpoints and you're trying to find, I capture an initial view, let's say from the front of the object, and I, for each of these different points, calculate the number of unknown voxels that would be captured if I captured that view. And they had some very novel methodologies for handling underpowered computers at the time. They had a very fast methodology for calculating the number of border walls between different views. It was overall a very impressive work at the time, but this work really was limited to only views around a sphere. It was not considering going inside of the sphere or potentially occlusions that might occur due to environmental restrictions. And it's also not considering certainty. So it's just assuming that if I observe it, I'm going to enhance my predictive model. Another work in 1995 was using a cylindrical model where it projected the face of the object into space behind it to find a volume of void. And what it would do is, in this cylindrical model, identify a next position that would reduce the void volume by as much as possible. Most of the time, however, though, the 180-degree view was the best one in this simplistic model, and really did not take into account that objects are a lot more complicated than this, at least household objects. In research, we find that most of the objects are pretty simple because they just end up being cubes most of the time, but that's an unfortunate oversight. And limiting this to a circular set of viewpoints just isn't good enough. Additionally, RoboScan in 2004 was trying to find a really efficient way to scan objects in museums. We might want to capture, let's say, a statue of a pharaoh and to turn that into a really high resolution model. And they were trying to develop an algorithm for not capturing redundant information at every single scanning point. And so they used about 1,000 views per view in simulation to determine if there are holes in the model to find a vantage point that would capture information that might be missing from the current view. But they never really specified how the view candidates are used for rendering, and I had to assume when I was reading it that they were randomly generated from a probably probabilistic model. And they're also really not considering certainty that particular voxels are filled or occluded. So the pipeline of the methodology I'm proposing is we first navigate to a particular object of interest. We capture the initial view. We get an initial completion of the object. We compute the uncertainty and find the next best view of the object. We capture that secondary view, and we complete using those two views, and then we actually go ahead and pick up the object. And I'm proposing that the object is just going to be whichever one is closest to the camera viewpoint at the final location. I could do something more complicated. I could be a lot fancier, but I do want to graduate before I die. So that's kind of what I'm trying to do here. And so take, for example, this rubber duck. This is a partial view, front of the rubber duck. And we get a voxel certainty model using our original shape completion work. And you can see this completed model that I get after running through the shape completion. But I have some uncertainty. You and I might have some intuition that the back of the duck is going to be filled, but the robot has only maybe a 50% chance that that's filled or not. And so what I'll do is I'll shoot a ray from the centroid of the voxel grid through that region of uncertainty. And I want to capture another view that will then say, oh, okay, that voxel on top of the back of the duck was actually empty, but the bottom was filled. And so we get a better idea of what the final model is because we captured that secondary view. And we can take advantage of this deep learned model to predict the geometry of the object. And so two different neural networks are going to be trained. One is going to be trained on the initial view of the mesh, and then the second one needs to be trained on both a secondary view and an initial view. I would love to reuse the first one twice, but neural networks are only really good at doing things that you've trained them on doing. They're not very good at inferring information or doing things that you have never shown them before. And so how am I going to evaluate it? Well, I need to test in simulation that I've captured the initial view, I perform the completion, and then I capture the secondary view. I will use the Jacquard and Hausdorff metrics, and basically what Jacquard is doing is it's doing a union over the voxels to figure out how many of them overlap with each other. And it's just trying to maximize the overlap of voxels in the completion and the prediction and the ground truth. And then the Hausdorff metric is measuring the distance of the surface of the two meshes, so the ground truth mesh and the predicted mesh. And I can use these to evaluate how my method is doing versus another methodology. And also I will use a local plan to find the next best view to be completed. Additionally, I have some novel ideas of how to integrate the earlier work of doing navigation to predict the next best view and then navigate there automatically. But that's preliminary and doesn't sound very coherent yet, and I'm still working on that. The GRASP plan will be generated using GraspIt, and GraspIt is software we've written to basically, it uses a simplistic model of a robot hand to find good grasping orientations of an object given its geometry. And I will evaluate how good the completion is by how good the grasp was, where I'll have a expected joint angle from the completion, and then I'll have an observed joint angle from using the ground truth mesh at that position. For that grasp. And so some initial work I've done to evaluate how my methodology is if we use depth-only information using the initial work from Jake Varley, which wasn't considering any kind of next best view or additional information above the single view. We get a joint error of 5.42 degrees, which just means that when I executed that grasp, it was 5.42 degrees off on each of the joints. The Jacquard was 89% overlap, and the Hausdorff metric was 6.5 millimeters off. So these are pretty good results for what they were. But we got better results when we added tactile information, and that's just basically tapping the occluded side of the object to get a secondary view. And then additionally, we can use the certainty of the voxels to dictate where to touch next. And I got even better results over our initial work using depth and tactile. So what I've been proposing is doing a secondary view, but to sort of justify doing this research, I did a detour and took a look at tactile information and touching the object. And if I have time, which I hope I do, I will use next best touch to evaluate how effective these things are. And that's just having a robot agent tap the side of the object that the camera isn't able to see, which can be a little bit faster than, it can be faster than moving the whole robot around as if I can just touch it. How am I going to evaluate it? Well, experimentally, I'm going to navigate through the Matterport 3D and Stanford 2D 3ds environments. And then the objects will be placed in simulation for the robotic agent to actually navigate to. And then we will do the grasping and simulation with the next best view completion. And then I'm going to capture the sixth floor of Sepser to evaluate our methodology in simulation in Sepser and then translate that agent to the real world using objects from the YCB object data set, because we have those in the lab. And then the agent will be tested in its ability to navigate to a particular goal region. This experiment will be recreated in the real environment once it is deemed reliable enough in simulation to not break the robot. And I will be done with my thesis when the real world agent can perform a grasp on the object using this proposed method. So my contributions here are a novel navigation pipeline where an agent learns to navigate to a color, depth, and semantic goal. We don't need GPS, compass, map, or relative position at goals at runtime. We're utilizing a novel panoramic goal, and we're utilizing semantic information during training for increasing information inputted into the neural network, and a framework to efficiently generate optimal expert trajectories in the Gibson simulator using a 3D scan of the environment of interest. And additionally, we have a novel methodology for discretizing continuous trajectories into a series of forward, left, or right commands. For the shape understanding piece, we have a framework for integrating visual sensory data to reason about object geometry and enable robotic grasping. We have this novel next best view planning algorithm that we designed. We have this open source data set for training a shape understanding system using both initial and secondary view depth sensory information. And we have real and simulated grasping experiments using these completed models. And we're also increasing the resolution to 256 cubed over the 40 cubed in the previous work. We're utilizing point cloud fusion to increase the resolution of the original captured view, so that's concatenating that initial and secondary views. And we also are providing an open source data set so other people can try to do this themselves. And so this was the timeline as it looked like in January, but coronavirus became a real thing. So those spring deadlines are not really accurate anymore, but I'm still looking to finish by spring of 2021, hopefully December, January. And that is my talk. And those are links to various aspects of my life if you're more interested in learning more about me. Thank you for listening. I will take questions if ID allows it.
You're allowed.
Yeah.
I have a question. Thank you so much for the talk. I was wondering, is most of the research right now going on in perception, or even would you say deep learning or machine learning helps a lot in planning and manipulate? What's the third thing? Planning and manipulation. Yes.
It's definitely largely deep learning. Deep learning is a really surefire way of getting a publication right now. And so most of the research is definitely looking into how can we learn a model rather than use a heuristic or an algorithmic approach. I think in the future, the really impressive methods are going to find out how to do both really well. But trying to get a deep learned method to handle vision is just better in general right now. Does that answer your question?
Yeah, I was actually also wondering, besides vision and robotics, there's also like planning the trajectories and that area of research, I think, which you kind of mentioned. But would you say most of the research activities going on is in vision and perception in robotics? Or even
say a lot of it's in grasp planning and manipulation. The vision, there's a completely different community called the computer vision community that handles the perception. And they're usually trying to see how can I create an accurate model of the real world in simulation for various tasks. Eitan Greenspoon, for example, is a researcher at Columbia that does that. It's, robotics is such a complicated field where you could be doing developing of the actual robot itself, or the sensors for it, or you could be programming them, or you could be controlling multiple of them at the same time. It really boils down to what niche do you plan on solving yourself? I program them. I see a lot of people trying to solve the programming problems. But there's a researcher for everything. So they're doing all of it. There's a researcher for every single problem, for perception, for manipulation, for planning, all of them.
Okay, thank you.
Yeah.
David, there's a question in the chat box.
Oh, in the chat box. Where is the chat box? Chat, more chat. Is there a limit for computational complexity you are using for still ensuring real-time action for the robot, or is it pre-computed and takes a while? How did you determine your maximum computational complexity for your algorithm? There is definitely a limit for computational complexity, and what it's typically restricted to is how big your model needs to be. Does it need to run on a GPU? Can you stream the information fast enough from the camera to another computer if you need to use a GPU, because most robots don't have GPUs on them. In our case, we're using simulation and everything's running on the same machine. So we were not really considering how complex the network has to be and how real time it has to be. But for impressiveness, real time generally has to be that each step is computed in under a second in order to get semi-real time looking performance for papers. And when I'm going to be running this on the real hardware, I'm going to have to optimize for streaming, for computing the next step for the agent. And we definitely cannot have everything be pre-computed when the agent is kind of doing things that it hasn't seen before in the trajectory at real time. But it's an excellent question, and something a lot of researchers don't ask because it's not a very sexy problem to solve. You're typically trying to make the algorithm as high accuracy as possible, but you're never really, people aren't rewarded for making things that are performant, I've found.
David, I have noticed with the participants, there's a lot of undergrads in the call, which we definitely are very excited to have you guys, and wanted to really have these calls so that these students can talk about or learn more about the process from undergrad, maybe, or master's to PhD. And given that you did your undergrad at Columbia, you obviously know that path a little bit better than maybe I do. So could you talk a little bit about like what that process looked like for you, kind of staying like on campus, maybe looking at other programs as well, and then kind of looking at different faculty that you wanted to work under?
Absolutely. So the way it worked for me is I was a very excited senior at Columbia, and I was doing research for a professor in programming languages and translators. And he proposed the idea of doing the PhD to me. And it kind of took me aback. I was very excited by the proposition at the time. I was actually about to start an internship at Goldman Sachs at the time. So it was on a very different trajectory from where I am now. And it was one of those things where I asked myself, after 5 years, would I be more impressed with myself if I had a PhD or I worked at a bunch of different tech companies? And personally, the answer was with a PhD. He also recommended I read a book called Getting What You Came For, which is, some of the topics in it are a little outdated because it talks about personal digital assistants a lot and calendar apps being revolutionary, but has some very good ideas of evaluating whether or not you really want to do the PhD, or it's just kind of a feeling that you have. And so I read it. I thought I did want to do the PhD. And I was doing research for him, and I was doing research for Peter Allen, my current advisor, at the same time. And Peter Allen also was interested in working with me, and he had an opening in the PhD program that he was willing to bring me in. And so one of the suggestions I would have for any of you considering doing a PhD is find a professor at Columbia, find a professor elsewhere that is doing research that you're interested in, and just ask them, I'm an undergrad, I'm willing to do some of the groundwork to enable your research. Can I work for you? And hopefully you can try to maybe get a publication. Having publications really helps your chances of getting in. I personally did not look at other universities because the path kind of worked out for me. But had I would have been a relatively good candidate because I had a bunch of different work I had done previously for different professors. I had worked for Simha doing FPGA design for Litecoin mining. I worked for Professor John Kender on user interface design. When I worked for Stephen Edwards, who's one of the professors that also was interested in working with me, I was looking at designing a compiler from OCaml down to, from Haskell down to a hardware circuit, and how can we do loop unrolling. All of those reports are up on my website if you want to look at those. It just really depends on the field that you want to go into. And so when I started working with Peter Allen, I realized robotics was a lot more exciting and a lot more marketable, and that's the one I pursued. Just really depends on what you're trying to get out of your career path. One other thing I would suggest, that if you're looking to do a PhD at a particular university and maybe you don't get in at first, that if you can do a master's at that school and try to work with a professor, a lot of times they'll graduate you to a PhD student after the fact, after you finish the master's there.
Can I ask how helpful your systems background was for robotics?
Extremely. In fact, if you do anything at Columbia, it's to take PLT, take operating systems, take databases, take as much coding as you can, because the thing that will differentiate you as a PhD student is your ability to code well. I see lots of code, which is called research code, purely because of how distinct it is from normal code, that just does not have software engineering in mind. It's not maintainable. It will only work for that particular problem. And 6 months down the line, you guys may have faced already, you don't recognize the code that you wrote anymore. You don't remember doing it. It's even worse if you don't have any kind of systems background. Take as much systems as you can while you can at Columbia. Those courses are really good. Analysis of algorithms is really good. Programming and problem solving was a lot of fun. I took a parallel GPU computing course by Michael Reed. He also taught computer graphics, and that was really good. That's what I would recommend.
Did you take all of those courses as an undergrad, or are those classes you also took in the beginning of your PhD?
So fortunately, because I kept going to Columbia, I really didn't have to take a lot more classes. So those are courses I took in undergrad. Some of those courses I tried to take early on in my Columbia career, like as a sophomore, I tried taking Jason Nee's operating systems class, and I just did not have the Unix aptitude to take that class. I also tried to take Alfred Aho's Programming Languages and Translators course early on, and some of those concepts didn't click for me until I became a senior, and I was able to actually more accurately and more entertainingly participate in them. I did like taking Jay Wu Lee's version of operating systems as an undergrad because it had more Unix information. But if you take them as a master's, it's not really going to matter. All I recommend is that you take them, period. I don't care when you take them.
Like you said, the order is sometimes important. So is there a particular order in taking these classes that you recommend?
Order. I'd say, I mean, you have to take advanced programming before you take any of those. If you're an undergrad, if you're a master's, taking advanced programming is a little more complicated, of course. You know, PLT just makes you a better programmer because you understand how to optimize code better. GPU computing made me better at identifying how to parallelize things and make things more performant. Computer graphics made me really good at C++ programming. There are things that just help you. It does not matter when you take them. Of course, you probably don't want to take operating systems and PLT at the same time, but I'm sure many of you already know that.
Any other questions?
I will answer anything. If you want to just like ask me about my hobbies, I'm down.
Do you think that you just like kind of immediately knew your inclination towards what you wanted to focus in terms of like research? And was that based off your classes, or do you think was that something like you picked your classes because of what you were interested in, and how did you figure out what that was?
Well, I liked systems. I really enjoyed doing coding and designing software and making things performant. And so I, tried to do that as much as possible. But for my research, one of the most important things that I've found out about myself is I like to do things that look impressive and sound impressive to people. And there's a lot of opportunity in robotics to sound impressive. And a lot of it involves marketing and understanding how to market your research so that people are interested. And so I've purposefully chosen a lot of research that is graphically interesting. I have this, I have these figures, I have these videos that I would otherwise not have. And so what I would recommend to you is find something interesting, find a way for it to sound interesting to other people, and focus on that. When I had done work on doing Litecoin ASIC design as a sophomore, I was just really excited about Bitcoin and cryptocurrency stuff. It was just fun. Other people were interested in it, and that's how I did the research project on it. It just kind of depends on what you're trying to do. Does that answer your question? Maybe?
Sure, yeah.
All right. I'm seeing a question here. Most fun side projects, internships you've done. Well, I've had two internships, both of which are at Goldman Sachs. I did some very fun things while I was there. I got third place in a foosball tournament. I made this game called GS Go because Pokemon Go was really popular at the time. So where you caught interns and people were playing it in the firm, and that was pretty fun. My most fun side project, I'm building a tablet from scratch right now. It's back there. So that's kind of fun, but I've done a lot of different things. A lot of them are on my GitHub. If you're curious as to what I've done. Stimulating and challenging projects would be maybe just start doing some stuff with deep learning. I think there's some really cool things that you can do really easily, like label images as particular classes, or predict, or maybe some of the style transfer GAN stuff. This waifu is not real is a really funny project, or the YOLO 9000 categorical labeling project is really fun. There's all kinds of different things you can do. And if you have ideas, I'm happy to help you figure out how to do them and help anybody kind of plan these things out. What classes helped you in designing FPGA besides fundamentals of CS? Oh, I did forget. I took what is it called? John Hui, who I think is here, knows the class taught by Stephen Edwards. No, not computer architecture.
4840 embedded systems.
That one, embedded systems. I took embedded systems, and that class was really awesome. I built a chip 8 emulator on an FPGA. So I built basically a whole computer that ran on an FPGA, and that was super fun. Highly recommend that. Yeah. Fundamentals was definitely not as useful for FPGA as 4840 embedded systems. I'm a CDN online master student interested in part-time doctorate while working full-time. Any thoughts on the value of a doctoral program while you are working full-time, or is it only worth it if you are in person and focus solely on a PhD? You know, it really depends on what kind of doctorate you're going for. Are you getting a doctorate so that you can get better career opportunity? Are you getting a doctorate just for fun? You know, a PhD, you get as much as you put in. It doesn't create a lot of value for you. You have to really invest a lot of time and effort into it. And the more time you invest into your thesis and developing the software for your thesis or developing the concepts for your thesis, the more people will take a look at it and the more you'll create a name for yourself. So I would say read Getting What You Came For. I'll get a link for it. Getting What You Came For book. It's a inexpensive book. You can buy it on Amazon right now. I don't get commission for it. I just really like the book. I highly recommend you look at that and figure out how much you really feel like you need to devote to it. Who do I look up to? Anybody taller than me. But in seriousness, I would say I look up to my parents, my grandparents, my advisor. There's plenty of people to respect in the world. I'd say I liked Elon Musk before he started getting so weird. You know, there's a lot of cool people in the world to get excited about. Any other questions?
I've heard that PhD programs can be quite isolating. Is that true in your experience? And how has the PhD program experience felt for you throughout your time?
Yes, it's definitely isolating. And one thing that's really important to keep in mind is the PhD is only as rewarding as you make it. It's really hard because people are usually not going to pat you on the back as much as you might be used to in other contexts. It really depends on your advisor and the kind of atmosphere that your lab has. So there are some labs at Columbia that have, you know, tens of PhD students and then, you know, tens or even, you know, maybe even 50 master's and undergraduate students. And those labs have so many more people that it's kind of hard for it to be isolating. So it just, in my case, my lab has 2 PhD students. There's really no strict schedule about who's in the lab and when. And so I've kind of had to create my own friend circle. I've had to create my own work environment. And a lot of those hobbies that I showed at the beginning of the slides, those were in an effort to try to be more social, get out more. You can't do comedy in New York without being social. You can't fly a plane without talking to somebody. My recommendation to you is it's a self-serving school, largely, at least at Columbia. And if you want to be social, you have to put yourself into social situations. They're not going to put you into them.
Thank you.
Mm-hmm. Anybody else?
What kind of companies or projects do you aspire to after PhD?
Oh, Boston Dynamics is pretty cool. Google's got some good stuff. Toyota Research Institute looked pretty cool. Amazon Robotics. There's some very cool companies in Finland doing robotics. There's a hedge fund in Long Island, I think called Republica, that only hires PhD students in STEM. They don't hire anybody in the financial industry, which looked really cool. There's all kinds of different people doing cool things. And I'd kind of be excited to work with any of them, because one thing that I know about myself, at least, is that a lot of problems in computer science all look the same when you boil them down. They're not that different. They're all code. And if you look at it that way, it opens up a lot more opportunity for you to do fun things.
How important is the prestige of a PhD program? And how does it matter if it's a maybe not as prestigious of a school in terms of the kinds of research, how interesting it is, and how interesting the classes are?
Absolutely. So I think your PhD is as valuable as you are, and it also helps if your advisor has a name. So there are plenty of really, really good researchers out there that are not working at the top 10 schools that are really good to work with because they are the #1 researcher in that field. So you don't have to get into the best school. It also depends on what you plan on doing with your PhD. I personally am going into industry 110%. I'm not going into academia. And because of that, it means that I don't really need to worry about the prestige as much, because I just want the PhD to enable the opportunities that having a PhD enable me to do, which is to give me more clout if I start a company, to offer research jobs at a particular company I might be interested in working at, and potentially get a higher salary at the end of the day. So no, you don't have to worry about prestige. Just do whatever makes you happy.
Awesome, thank you.
Your PhD is 3 years long, which is kind of shorter than usual. So is there a reason, or can that be done in certain exceptions?
Well, so mine's actually 4 years. I graduated in 2016. I started the master's and then kind of was already doing research. So when you do the PhD, you kind of include the master's. But can it be done that short? Depends on your advisor. In my case, my advisor likes to push people through the program, and that's how he has historically done it. There are other advisors that like to hold on to PhD students for 10 years. I don't recommend you do that if you can help it. But take a look at the timeline of other researchers from that advisor, and you'll get an idea of how long you should expect to do yours. I think he did have one student that literally finished in the minimum amount of time, which is 3 years. You need a minimum of 6 semesters to finish the PhD. At Columbia, anyways.
This is super helpful, thank you.
Of course.
Anybody else? I know David when he says he will stay here all day, so I want to protect his time from himself. But like I said, everybody, thank you for joining. This was recorded. If you want to watch it later or refer to anything, David, I'm sure also would love and welcome any questions that you guys have via email, which he put in his last picture. But thank you guys for joining again. I hope this was very helpful. And I think especially having the angle of going through undergrad to a PhD was definitely insightful for everybody, David. So I appreciate you volunteering. Anything else that you guys have before we sign off? Cool. Okay. we are joining again next week. I will send out an email, and then of course be sure to join our Tuesday Topics with alum as well, which I will also send out via email. But I hope everybody has a great weekend, and thank you again for joining.
Have a good day.